Lecture 1.11 is about temperature scales, the history behind them, and the continued discussion regarding measurement of energy through temperature. Any case, we're going to start a discussion with the Fahrenheit scale, the earliest of all the scales, and we're going to talk about its difference in terms of the Celsius Kelvin. Now, we still in this country still use the Fahrenheit scale, which of course is the oldest, okay, English kind of unit still used. The BTU that we talked about was the amount of energy it takes to raise 1 pound of water 1 degree Fahrenheit. And even James Prescott Joule himself was using Fahrenheit when he was figuring out how much stirring would cause in terms of foot-pound, 1 pound of water to go up a degree Fahrenheit. So this is the oldest, okay? Celsius and Kelvin are the current scales that we use, and they are used interchangeably. We'll get to that. And the SI unit, of course, is Kelvin. Notice there's no degree there. Okay, so let's talk about the Fahrenheit scale and where it came from in terms of history. I believe if you understand the history, you understand more about how this all fits together. All right, so Daniel Fahrenheit, okay, in the early 1700s was the first person to make a pair of thermometers that read the same temperature. Before 1714, there was something called Florentine thermometers. And let me give you an example of some Florentine thermometers. And here's a bunch of different ones right off Google Images. And if you look, they look very interesting. Let's just open up to say this one. And let's talk about it and how it works. Very simply, what they were was a jar filled of alcohol. Sometimes wine was used because, of course, alcohol's in wine. They had an air, okay, and basically you had a liquid level here. It's not a barometer. It didn't measure pressure, but as temperature goes up, these liquids expanded and actually climbed up higher. Okay, in fact, I have one in class that I'll show you. Another one here is an open container filled probably with wine too, and it was the alcohol that moved a lot. In any case, temperature increased and these liquids expand up. This is an open tube, a Florentine thermometer. In any case, what they would do with these, and these were just novel things, little tiny tubes these thin tubes were hard to make at the time, but they were very interesting in that the thinner the tube, the more movement you would see. And again, all they were novelties. You could make a mark for the lowest temperature or the lowest of that time that you had the thermometer, and you could mark a highest point, and you could talk about how maybe the temperature differed between those. But we didn't have units, we didn't have thermometers that measured the same thing. They were just novelty things. All right, so back to where we were, getting back to the Fahrenheit scale. So what did he do? How did his scale work? Well, for him, and he wasn't the first one to think about this, a guy named Isaac Newton, who you'll hear a lot more about in your quest in science, first thought that we should base the scales of temperature, okay, based upon some fixed points, and that was very, very important. So this idea of fixed points was something that Daniel Fahrenheit thought to use. Now, he was an inventor, not so much of thermometer. He was the inventor of thinking about applying them to fixed scales. He was born late 1600s in I guess, I don't know what, it was a Polish city, I guess, at the time, so I guess he would be called a Polish man. In any case, his mother and father died of eating poisonous mushrooms of all things, and he was given to the state, awarded the state, to learn apprenticeship in something, I forget what that was. But he got interested in seeing these thermometers and basically ran off. Instead of learning his apprenticeship in some area, I think it was bookkeeping, he went off to build thermometers of all things. But thermometers that were able to measure the same temperature. So he was fascinated about that. Any case, what did his scale mean? Where did it come up with? Well, it started with this idea that he took a temperature and he found the coldest possible temperature to be a salt and an ice mixture. So he took equal amounts of salt and ice, and he found it to be lower than the freezing point of water. We'll talk more about that. But he had a certain salt-ice mixture, the same mass of salt, same mass of ice, and that type of salt lowered the freezing point. Okay, and he called it the coldest possible temperature based on this arrangement of equal mass of salt, equal mass of ice. He called 0. And then he found the freezing point of water. He figured that was a fixed point too. Again, he was the idea of taking fixed points, and he made that a 4. Okay, and that was the freezing point of water. So water in the freezing point. Okay, that was his fixed point. Okay, next step, he said, well, I need another high one. So he figured the temperature of the body didn't change. So what he did with his Florentine thermometer, I think, is he measured how low it went for a salt-ice mixture, marked at 0, and then somehow figured out these 3 temperatures and divides them by 12 markings. Okay, and he made 12 to be body temperature. Now, it seems kind of odd, a 0 to 12 scale. And he made equal markings, so there was actually, 4 markings in between here, and of course there was more. Now this is not drawn to scale, but that's how he came up with it. So we had a 12, 4, and 0 scale at first. And we said, why in the world would he come up with this? Well, this is late 1700s now. He was an inventor. He was actually a good traveler when he was running from the law, when he ran away from his apprenticeship. The police were actually after him. He was in many different cities, and he saw that people were coming to the cities. They were building up, and people were getting quote unquote, it was before the industrialized period, but people were starting to gather in cities. And one of the novel things too was watches. Okay, handheld watches were getting to be very common for, the aristocrats or the people that would gather in cities. In any case, people were starting to care about time for the first time. Why? Because, well, we needed to start gathering people in factories eventually. So time was an issue. So if you think about a clock, okay, that's what he was thinking about in terms of it, some sort of meter, we think anyway. So he was trying to base his system on a 1 to 12 scale, like a clock, like a watch. Believe it or not, the early 1700s, pocket watches were very prevalent among, of course, the wealthy and the aristocrats and people, okay. And what the time was for the first time in our society was very important, because now we needed to have people start gathering in these areas to do important work. Okay, what time you're going to see you, okay, as opposed to you started just worrying about what you're going to eat that night. Okay, that being said, so it was 0 to 4 scale, 0 to 12 scale didn't work out for him, okay? So what he did was, or at least he didn't, we think anyway, because we don't have this discussion, we think that what he did was, and let me just get rid of this, he got rid of this 1 through 4 scale that we all know what it's based upon, and he times it, okay, by everything by 8. This gave us our 96. This gave us our 32. And this gave us, of course, by 0, still 0. And that you can see where the weird numbers came from. Now, during this time, when he did this, okay, he was working with alcohol thermometers. Okay, like I talked about with the wine and the open tube thermometers. Okay, they call them thermoscopes in any case. And this is the system he had. And at this point, we think that he started working with mercury thermometers. And you can measure the boiling point of mercury thermometers. And of course, okay, you would get higher temperature, and eventually that was 212. Okay, so at this point, he went to mercury thermometers, and we got the boiling point of water about 212. And you say, okay, why did he multiply everything by 8? Why was that? Because again, Fahrenheit numbers seem to be weird. 32 degrees, well, now you know where it came from for freezing of water. Of course, this is the freezing point of water. I erased that, so let's put it back. And this, of course, is the salt water ice mixture, so salt ice. I already see my video's getting too long again. I'm getting wordy, sorry. And of course, here is the body temperature. Now, if you notice, the body temperature, 96, isn't what we expect. It's 98.6, so we had to make some adjustments later on. But again, I guess he just put his thermometer under his armpit, and that was good enough. Now, again, why these weird numbers? Why did he multiply by 8? That's the question. And our guess is, if you check out the difference between 32 and 212, you subtract that difference, you will see that there's 180 degrees. He was trying to build a scale on a 180 degree scale. Now why? Well, again, he was an inventor. The clock didn't work out, but he was thinking about a scale, okay, that would go from maybe 0 maybe to a 180 degree scale that would measure temperature. He was thinking about, a simple gauge, a half circle gauge, we think. So his scale is based on 180. All right, so that's where the numbers come from. And now, of course, this 96 was adjusted to 98.6 later on, okay? But let's clean all of this up. And oh, that didn't clean everything up. Let's just say erase it all. Boom. Okay, and let's go back to this. So this Fahrenheit, okay, this was the coldest temperature. Okay, this was that he dealt with. This was his 0, which was a salt-ice mixture. All right, and this was the freezing point of water. He made this 32 degrees. And this was, of course, 212 for water. I know I was using that for the body temperature, but now that's for the water. So this is the boiling point of water. This is the freezing point of water. And this, of course, is the salt and ice mixture. All right, now this temperature here will come later. And notice we're using degrees. Degrees represent we're using some kind of scale. A degree is some kind of is the amount between a calibration. All right, and again, he was Daniel Fahrenheit, given the invention of the thermometer or the thermoscope, in that he was able to, for the first time, build thermometers that could measure the same temperature. So after his work, people started saying, as opposed to saying, hey, our thermometer is saying it's reading a little higher than it was last year on this date, we can say with quantitative, not qualitative, quantitative numbers, hey, it's exactly 70. Yesterday it was 69. How much warmer was it? So this is an important tool. Okay. Now Celsius, Andy Celsius. Okay, this guy was a Swedish man who dealt with, was a physicist, he was an astronomer, all different things. But he grabbed a hold of this concept of what? Fixed points. And that's what started fixed points to make a thermometer. But he didn't like this arbitrarily 32 to 212, 180 scale that Daniel Fahrenheit was using. So what he did was he made things simpler. He said, let's take the freezing point of water and let's take the boiling point of water. And let's make 2 points. And let's make it 100 degrees in between those points. That's why they call it a centigrade scale. So we made 100 degrees in between those 2 points. The boiling point and the freezing point were still the same, okay? But the work that he did carefully, he realized, though, that the boiling point and freezing point, okay, depended upon pressure. So he did a lot of work to figure out what the exact boiling point of water was and the freezing point based on pressure differences. But then he made a scale based on 2 points, you know. And the weird thing is, his boiling point he called 0, and his freezing point he called 100. So it went backwards in his scale. He was lauded for a new, easier scale. Interesting enough, a year after his death, they changed it back, or someone said, well, let's make this a little better. Now that he's not around, we probably just do this. Let's make this 100 and make this 0. I'm going to use degrees here because he used what? His degree between 2 points on his thermometer was some value that was different from Fahrenheit. So that's why we use degrees. Okay, and this of course occurred, I believe, in the 1740s or so, 1738. Okay, and then much later we had in the 1800s, 1848, so to speak, and the dates are important. I'm trying to give you a historical framework here. 1714. Okay, this is 1738, so this is a little after Fahrenheit. Then we have almost 100 years or so, I guess in this case 110 years transpired, and we have Lord Kelvin. And Lord Kelvin is also called William Thomson, and he did very important work here. We're going to do a lab. He said, okay, I like this system, Celsius, and I really like your system of 0 to 100, and I'm not going to change the size of your degree. Very important. He's using the exact degree size that Andy Celsius has. Notice there's no degree here because Kelvin didn't come up with a new value, new amount between 2 lines. He was using the same designations, meaning from the freezing point of water, okay, to the boiling point of water, there was still 100 units. So the size of the actual Kelvin and Celsius degree, notice I don't say degree for Kelvin, is exactly the same. Well, his work was, he didn't like all these negatives. He noticed that there's so much temperature below this, and he didn't like all those negatives. So what he did was, let's make everything positive. So what he did was very, very important, and I'll explain this very, very easily. He measured pressure and he measured temperature, and he noticed that as temperature decreased, which is we all know now is motion, he noticed the pressure had to decrease. He looked at that and said, wow, there's a linear relationship. Now he did, of course, 1,000 different, measurements, but he saw that temperature and pressure. Now we're going to learn is pressure is the force of a molecule colliding with something. It's a force over an area. Okay, well, guess what? It's about movement. If temperature slows down, as we go to the left, here's temperature, motion slows down, so the amount of collisions decrease. It kind of goes together. Now, he couldn't measure over here, but he postulated, wait a minute, if I can make these guys if I can get some kind of linear relationship, couldn't I do a regression line or extrapolate that to this axis here? And he said, yeah, this must be the coldest possible temperature. When there's no more pressure, there's no more temperature. Okay, and he found it to be negative 273 degrees Celsius. And all he did was, okay, using the Kelvin scale, knowing that this mark here and this mark was 273, he made his zero not here, but he made it at the negative 273 mark. So again, the coldest possible temperature that he found by extrapolating pressure and temperature was negative 273, which we now call absolute zero. Now, why is it absolute? Because at that temperature, there's no more motion. Therefore, there can't be any more collisions or pressure. So what he did was, let's just make this very important clear, okay? Or he made this the zero. He just put his zero that was here for Celsius 273 degrees sooner, okay? So let me just get rid of some of this stuff here. It's in the way. So what did he do? This was zero. This was 273. And this, of course, is 100 units, right? We're still using the Celsius degree. That's why there's no degree here. It's just 373 kelvins. So all he did was start the Celsius degree or the system sooner. So why did he want something that was absolute? Because he figured a zero should mean what it says, and it doesn't in the Andes Celsius scale. There's plenty of pressure and motion at zero. Besides, he didn't like all these negative numbers in between that would mess around with calculations. So Kelvin equals Celsius plus 273. This is given to you in table T of your reference table. It's a conversion on the Regents level. Now, your homework was about finding these two formulas. I'm going to give you them if you watch this, and you can continue working with the homework. Okay, but please, it's all about deriving in the formula. So I'm going to give you these, and we'll work forward, and I'm almost done. Okay, so Fahrenheit you should have found, okay, is equal to 1.8 Celsius plus 32. And that's what you should have gotten, okay, from your homework. Celsius, although you didn't get this directly, if you solve for it, is equal to 1 over 1.8, that's the inverse, Fahrenheit minus 32, and this minus 32 has to be first. And before I let you go, okay, I just want to talk about the differences. These formulas are something you don't need to memorize. You should be able to derive. Okay? Now, how do we derive them? Well, if you look, if I want to get a Fahrenheit from a Celsius, if I'm starting over here, party people, let's go to magenta. So I'm starting over here in a Celsius scale, and I want to make an ugly arrow like I'm making, okay? And I want to make a Fahrenheit from a Celsius. I'm timesing it by 1.8. Well, why? Isn't 212 1.8 times 100? Absolutely. We have a scale, okay, that's 180 times here. Here it's only what? 100. So I'm timesing it by 1.8. So I'm taking the Celsius and I'm timesing it by basically, okay, 1.8 to make the scale that was from a 100 scale, a centigrade scale, into now a 180 scale. That's why I'm timesing by 1.8. That's going to make sense to you. Now, why am I adding 32 is because the bottom zero number here, okay, the bottom number for Celsius is 0, but the bottom number, okay, for the same measurement is 32. And that should make some sense to you. All right. Now going the opposite way, what if I want to get a Celsius from a Fahrenheit? Well, notice, okay, the first thing I do is take my Fahrenheit and I subtract 32. Now, why do I do that? I do that to make sure that I first get into this Celsius understanding, because a 32 really is a zero. And to solve for the Celsius, I've got to subtract that 32 first, so that I'm in the scale, in the kind of number that can be evaluated. And then, of course, I do the inverse of 1.8 to get that. So these two values, or these two formulas, should be able to be derived by looking through them. Okay, and you should be able to figure what the coldest possible temperature is, and you should be able to give me that number for Fahrenheit. Obviously, I didn't put that in when I was talking about Fahrenheit. Why? Because the discussion of the coldest possible temperature did not begin until Kelvin. Okay, so the rest of the ditto you should be able to clean up and finish and do the conversions. Okay, and again, very important conversions. Remember, when you're doing conversions, you're maintaining significance. Okay, rock on.